Hello everyone, here's Ray from UCSB. I'm going to introduce our work M3L language-based video editing via multi-modal multi-level transformer. Nowadays, visual editing applications are widely used. For example, Photoshop serves to modify the brightness, the contrast, or even the content for digital art, and Premiere is a well-known video cutting and editing software. However, they all require prior knowledge and complex operations to accomplish such editing, which makes it difficult for novices to get started. Well, for humans, natural language is the most natural way of communication. If those editing tools can follow our given instructions and perform related actions, it can improve their accessibility a lot. For example, we can talk to Photoshop like, hey, a fire is in front of the girl, or tell Premiere like, move the number to the lower right, and they can help us to do the editing automatically. In this paper, we introduce a new task, language-based video editing, aka LBVE, that edits a source video S into the target video O, guided by an instruction X. The feature of LBVE is that we should preserve the similar scenario of the source video and modify the somatic in the target video according to the given instruction. For instance, in this case, we have to preserve the man and the background, but alter his gesture by the given waves down with his right hand. To perform LBVE, we propose the multi-modal multi-level transformer, aka M3L. In general, M3L takes the source video and the instruction to produce the target video. We get the preliminary linguist feature from the Roberta language model, and the frame feature by process the video sequence with 3D residual net. And our M3L is to model the multi-level cross-modal fusion between language and video. The encoder first adopts the local level fusion LF to extract important portion from each single frame with each word embedding, and the global level fusion GF extracts the entire video motion with the sentence embedding as the cross-modal feature. During decoding, the decoder also extracts the cross-modal feature for those previous generated frames. GF is first adopted to give the high-level concept of moving motion by the interaction between the cross-modal feature from source and target, and LF is then applied for detail-specific property provided from word tokens. So in summary, the transformer T models the source video frame and a given instruction and considers previous generated frames to acquire the decoding feature. And finally, the frame generator will scale up the decoding feature and produce the target video frame. And let's get deeper into multi-level fusion MLF. Both video and language are multi-level conveyed, where video is composed of a series of image frames, and language is a set of word tokens with a specific order. LF is to fuse between a single frame and each word token. GF models the entire video sequence with the whole instruction. And both LF and GF are following the idea of multi-head attention. And you can find the detailed computation process in our paper. To learn LBVE, we have two training losses. At first, the editing loss is computed with the ground truth target video by mean square error over the generated frames. We also consider the video quality through the dual discriminator, where the frame discriminator goes with the frame quality of a single frame, and the temporal discriminator works on temporal consistency for continuous K frames. Both of them are conditioned on the given instruction, and we follow the general gain that the adversarial training process can help enhance the quality of the generated video. And to evaluate this LBVE, we collect 3 different datasets, including 2 diagnostic moving MNIST and moving clever, and 1 e-gesture for the human gesture scenario. Moving MNIST is extended from MNIST, which will replace the specific number with the given one, or change the starting direction for different moving motions. Moving clever is built from clever that modifies the property, such as the color, the size, the shape, or the material of the specific object, and places the moving object into a particular given final position. E-gesture aims at preserving the same person in the same environment but altering the moving hand gesture. The natural instructions are all crawled from the Amazon MTurk. And here are some numbers and statistics about our collected datasets. As a brand new task, we do not have previous works, so we consider these 3 as our compared baselines by concatenating linguistic feature with visual feature for LBVE. Pixel to pixel performs frame-by-frame video translation. Video to video does this video to video synthesis also with the help of temporal discriminator. E3D LSTM treats the source as the video and produces the target video as video prediction. We have the following evaluation metrics. VAD is inspired from the French inception distance, aka FID, that computes the video feature distance with ground truth target video. Object accuracy and mean intersection over union are for diagnostic datasets that consider the accuracy of the modified object and the position match of the moving. Gesture accuracy verifies if the target video contains the correct type of gesture with the given instruction. And let's check the quantitative results. We can find that since pixel to pixel does frame-by-frame translation, it suffers from insufficient video tempo and results in the worst. For example, only 8.6 gesture accuracy on e-gesture. For video to video and E3D LSTM, although they attempt modeling video sequence, they still lack explicit cross-modal modeling. And in contrast, our M3L incorporates multi-level fusion between video and instruction and can achieve the best performance on all kinds of metrics across all datasets. And here is the ablation study. Firstly, we can see that the instruction is essential for controllable video editing. If there is no text as the guidance, the model has no idea how to edit it, and leads to a terrible result. For example, only 4.7 gesture accuracy. On the other hand, with both instruction and multi-level fusion, it can benefit the cross-model modeling between video and language with the lowest VAD and highest gesture accuracy. We also conduct the zero-shot setting to evaluate the generalizability. We filter out 10/40 number direction combinations of moving MNIST and 12/96 size, color, material, and shape combinations of moving clever. So for example, the model should generalize to the unseen blue circle, even if it only saw blue square and red circle. From the experiments, our MLF also helps generalization, even if under the zero-shot setting. We have human evaluations by Amazon MTurks here. Under 3 targets, video quality, alignment between generated video and instruction, and the similarity to ground truth target video, MLF all shows its advantage. The result also supports that this kind of multi-level fusion, where single frame to word token and video sequence to whole instruction, is effective for language-based video editing from different human aspects. We show some qualitative examples here. Our M3L can change the number or change the direction from upper right to lower right of the moving number. We can also modify the final moving positions or the property of the object into like blue color, rubber material, and cube shape. And of course, the hand gesture is controlled by the given instruction, where the motion is corresponding to such raise a hand or showing two figures from left to right. And that is all about our paper, M3L Language-Based Video Editing via Multi-Modal Multi-Level Transformer. Please visit the paper for more information. And here's Ray. Thanks all for your listening.